Hello, my name is Jonathan Wallace, and welcome to my lab 4. This lab is on bar magnets. In this lab, we measured the magnetic field of a bar magnet using a magnetometer on our phones. We measured the magnetic field at set distances away and found the strength at set distances, so we were able to calculate the drop-off of magnetic field at certain places. And using all this data we gathered, we found the correlation between the distance from the magnetic field and the drop-off of the magnetic strength, and used that to find the magnetic moment of the dipole magnet that we're given. And also, we're basing a lot of this lab on the assumption that we were given a bar magnet that's going to act as a dipole magnet. And from the correlation between the drop-off in strength and the distance away from the magnetic field, we were able to calculate what direction it's facing and the magnetic moment in order to calculate the magnetic field at other points that aren't just directly in front or behind it. So some prerequisite information that we might need to know. This formula, top formula, is relating the magnetic field to a change of position. So depending on the position, that will give us a separate magnetic field. And this is pretty similar to the magnetic field of a dipole moment that we were given, except it's not broken down into its parallel and perpendicular formulas. And then beneath that, we have the magnetic field equals some current multiplied by a change in length. This formula will be especially helpful because the currents in our electronics can actually generate a magnetic field and throw off our data. So if we don't account for this, it can end up messing with our data. And beneath that is a sort of distance dependence formula where the magnetic field equals some constant multiplied by the position or distance away it is from the magnet to some exponent, and that formula becomes really useful in helping us find the mu, or the magnetic moment, of our bar magnet. So our goal in this lab is to find the strength of a magnetic field from a bar magnet, and to do this we have to orient our bar magnet to be orthogonal to the Earth's magnetic field, and this is because that's the main way to cancel out the Earth's magnetic field, is to be orthogonal to it. And this helps us pretty much isolate the magnetic field from the bar magnet. And then we measured the distance at which the magnetic field from the bar magnet gave us a certain strength. And then we also measured the off axis at this distance. So we pretty much just went perpendicular that same distance and measured the magnetic field at that off axis angle. And then we used all this data to find the magnetic dipole and the strength of the on and off axis fields from the magnetic dipole. So like I said before, a lot of this data is plotted by the position away from the magnet and the strength of the magnetic field we recorded. And it turns out that data ends up being exponential. The magnetic field decays exponentially as you get further away from the magnet. So in order to get a cleaner curve, and this also helps our math later, we plotted the log of the magnetic field and the log of the distance away from the magnet as opposed to just the magnet and the magnetic field itself. So here's sort of a breakdown of that data. Plotting all of that data we were given, we're able to get this formula of y, which was the log of the magnetic field, equals negative 2.9324x minus 13.794. If you remember that formula from earlier, the magnetic field equals some constant multiplied by the position raised to an exponent. And so what we have plotted is the log of that constant multiplied by the log of that constant plus some additional factor. And so we know from this that the ln of k, or the constant that we're searching for, is negative 13.794. So for solving for this, we can end up with the constant and the amount that the magnetic field dropped per change in distance, which would be like the slope of the formula and the y-intercept. And then plugging this back into our formula, we can end up solving for the mu of our magnetic field. So before I get into the code in this lab, there are some assumptions and possible sources of error. So we originally assumed we were given a cylindrical bar magnet, and we're assuming that it makes a perfect dipole, and we're using dipole formulas. And also we're using a formula that gets more accurate the further away you are from the magnet. So we could be too close for this formula to be accurate. And other electronics could affect our data, because as you know, a current flowing through a moving change in electrons or a current can generate a magnetic field, and we only accounted for the Earth's magnetic field, not all of the currents in the laptops around. We tried to isolate it, but that could still be affecting our data. And also, our phones that we're using to measure the magnetic field has a chip, but it's not dead on in the center. We tried to account for the offset that the chip is from the edge of our phones, but there could also be that causing a minor amount of error. So to get our data for the off-axis magnetic field, what we did is we went the same distance away we did the first time, but then also went that exact distance above the magnet to find the magnetic field of some place perpendicular to the magnet's on axis. And we used this data to calculate another magnetic field and went through a bunch of similar steps that we went through the first time to generate the off-axis magnetic field. So here's some of my code and a snippet of the code running. For this lab, we had to write code to calculate the magnetic field at any position with a given mu, or magnetic moment. And we used the magnetic moment that we calculated earlier in order to use this code. And using that magnetic moment, you can see the results of the code up in the top right, where the magnetic field shoots out of the north pole, circles around in a sort of radial pattern, and goes back into it. And this lines up pretty accurately with what you should expect from a bar magnet. So like I said earlier, my simulation for the magnetic field, even though it's a bunch of independent points and not like lines connecting them, I hope you can still see the connection between the lines of the magnetic field that my code simulated and what you'd expect from a bar magnet, where it shoots out of the on-pole axis and circles back around in the opposite direction. And we can see that the off-axis that should be harder to calculate, it points sort of inwards to represent it flowing back into itself. And I hope that's all visible from my code. So we were given a couple of statements and see which one would hold true after we did this lab. So the first one we found to be true. The second and third were false, and the fourth was true. The general way to easily figure out which one was true and false was just like the magnetic field of the dipole relies heavily on where you measure it from. It decays exponentially. So we know that the magnetic field, when you're far away, it's going to drop, but it won't exactly be near zero, but it still will drop. And it's not independent of the x component. Like nothing's independent of its position. So to answer a couple of what if questions, what if we hadn't orientated this experiment to compensate for magnetic north? Well, in the magnetic field of the Earth, because Earth has a north and south pole, that magnetic field would have affected our data and thrown it off. And the data we collected is the basis of pretty much this entire experiment and code. So all of the rest of this lab would have been wrong if we hadn't accounted for that. And what if we were to stick two identical magnets together end to end? Well, that depends if we're facing north and south versus north and north. But if we're facing the magnetic north of one magnet to the south of another, the magnetic field at each distance would increase, and if you were to do the opposite, the magnetic field would weaken. Anyways, this concludes my lab. Thanks for watching.